The last thing that I want to discuss to wrap up the concept of radioactivity is the idea of activity. So activity has a symbol of A, but basically it means the same thing as decay rate, which we have learned earlier, which is negative dN over dt. Since activity has the same meaning as decay rate, we can say that A is equals to negative dN dt. Therefore, because we know that dN dt is equals to negative lambda n, we can change this negative dN dt over here to be equals to lambda n. So the idea that this equation is trying to propose is, if we have a greater number of parent nuclei or greater number of radioactive nuclei, we should expect that you have a greater activity. So what is activity? Activity, this value here, it represents how intense is the decay. Okay, so it means that if you have 5 decays per second, that's how intense your activity is. Okay, we're talking about the radioactivity. How intense is the radioactive activity? Okay, if you have an intense activity, that means there are many decays that happens per unit time. So let's say 1,000 decays per second is a greater activity compared to 5 decays per second. Okay, but actually you should think of it as the same thing as decay rate. There's no difference to it. It just give it another name, which is called activity. Okay, so why do you want to propose this this new quantity over here? It's because it allows us to derive a new equation to see how does the decay rate change with time, or how does the activity changes with time. So we have our initial equation, which is the equation that describes how does the parent nucleus change, number of parent nuclei changes with time. This is the equation that we have. We are going to multiply both sides with lambda, making it lambda n on the left hand side, lambda n naught on the right hand side. So now this equation here, we can relate it with the equation on the left by changing this lambda n on the left to be a, whereas lambda n naught over here will be the initial a naught. So now this will be our new equation, which we can sketch a graph, and the graph should let us know that the activity will decrease exponentially with time. Okay, so everything makes sense actually. Initially, you have greater number of parent nuclei, so there are many parent nuclei waiting for decay to occur. So you should expect that there will be more decays that happen at earlier times. At earlier times, there's more parent nuclei, so more decays will happen. So more decays per unit time, you have a greater activity initially. But that causes the number of parent nuclei to decrease drastically initially. Initially, it drops very steeply. So once the number of parent nuclei has already decreased, that means there are less number of parent nuclei waiting to be decayed. So because there are less number of parent nuclei waiting to be decayed, the number of decays that happen at that time will be less. There will be less number of decays that happen per unit time at a later stage of the decay process. So less number of decays happen per unit time is equivalent to us having a less intense activity. So you can see that the activity also drops exponentially with time. So you should expect that you should see the same graph for the number of radioactive nuclei against time and the activity against time. They should show a same graph, because this is the equation that we use, and this equation here told us already that A is directly proportional to N. So the type of graph that you should expect from them should be the same. Okay, so this is you can check back to the diagram that we have initially for this section. You can see initially we have number of parent nuclei or number of radioactive nuclei is 100, but let's say each frame over here represent 1 second has passed. So from the first second to the second second, you can see that the number of parent nuclei has already decreased by 63. So now you're left with 37 parent nuclei. So what can we say here? When initially n is equals to 100, our activity here is 63 decays per second. 63 decays per second. That's the initial case that we have. N is equal to 100, A is equal to 63 per second. Okay, but as you move on to later stage, comparing diagram 3 to diagram 4, you can see that the number of parent nuclei you have here is 17, but the number of this integration, or the number of decay, is 17 minus 5, 12. So in this case, at later stage, you will see that the n is 17, but your activity is 12. Okay, so 100 for n, 63 for A, that's the initial stage. 12 for A, 17 for n, that's the later stage. So you can see that the number of n decrease, at the same time the A also decrease. So this match with what we have discussed earlier in this graph. N decrease with time, and your A should also decrease with time, both of them decreasing exponentially. Okay, so that wraps up how everything relates to each other to study the process of radioactivity, and that wraps up our study on nuclear physics under the matriculation syllabus.